So let's look at the different things when we need to consider when we're graphing. So we've dealt with the zeros. Okay, these are kind of standard things that we do in grade 12. Then we start looking at endpoint behavior, which is like our limits as x goes to infinity or negative infinity, and those also give us slant asymptotes. Okay, so slant and horizontal asymptotes are to do with endpoint behavior. So we need to also look at critical points. So the ones that are easiest to kind of identify are when the slope is equal to 0. Okay, these would be potential max min points, but also where the f prime doesn't exist is very important. So I'm going to highlight that because where the f prime doesn't exist, we have to make sure that we're aware that that's a point of a critical point, and we have to test slopes across that point. Okay, so these could be vertices, non-differentiable points. It could be points of discontinuity. We can have holes. Okay, vertical asymptotes exist as well. We have to be careful of all those issues when we're graphing. So it's nice to, for the last 2 points here, this is basically our slope charts where we're doing increasing, decreasing regions, and where we can see concavity going up or down, and we can test for inflection points when we test across any points. Any changes in concavity represent an inflection point. So non-differentiable points that are not smooth and continuous. Okay, so we can have endpoints that we have to consider. Okay, those are easy to find. Vertical asymptotes, vertices when we have like a nice vertex, okay, smooth vertex like that. Okay, but we also have these issues of cusps, and cusps are these points where we have it kind of curving up, and then we just all of a sudden change direction. Okay, these could be kinks as well. So taking a look at where this function f to the x to the power 2/3, where it's not differentiable. Okay, so if I find a derivative here, this derivative is going to look like this. So it's just power rule. Okay, so there's our derivative. Now, because the x ends up in the denominator, okay, we have a non-differentiable point at x equals 0. So x equals 0 is non-differentiable. But what is happening there? Because we know that it is continuous at 0 because we have a point at 0. Okay, we know a point exists at 0 because that's part of the domain, but it's non-differentiable. So what's actually happening there is if we actually do a little slope chart. Okay, so I'm just going to do a slope chart here. So f prime at x equals 0, a coordinate does exist. At x equals 0, y is 0. But we have this non-differentiable point. And we can test what's happening here by just testing the slope. If I put a negative number into here, I'm going to end up with a negative slope. Okay, so it looks like it's going to go like that. Okay, and if I put a positive number into here, I'm just going to get a positive slope. I get like that. So what ends up happening is, and when we graph this, we're getting a graph that kind of is coming down and then going back up. Now there's curvature to this as well. Okay, and in fact at 0, 0 there, that's the point that's going to happen at. Okay, that is a non-differential point. It's a kink in the graph. And we can actually take a much closer look at this if we actually look at the second derivative as well. Okay, so we can justify what's happening with the first and second derivative in that testing my second derivative, I can see what's going to happen at that 0 point. Okay, so the second derivative looks like this. Using the power rule, I'm going to get negative 2/9 x to the negative 4/3. Okay, so I can kind of simplify this. This is going to be negative 2/9, and it's going to be the cube root of 3, so cube root of x to the power of 4. Well, any number plugged into here is going to give me positive, so we're going to get negative concavity for all of this, but it's not defined at x equals 0. So again, we have a non-differentiable point here. Okay, the second derivative does not exist at 0 because we're dividing by 0. But when we plug in, I have negative concavity on this side, and I have negative concavity on this side. So this is what's happening with the graph then. we end up getting a graph that looks like this. Okay, it's sloping down to 0, 0, and then it's going to slope like this from 0, 0. Okay, so that's what our graph's going to look like. The point exists at 0, 0, however, it's non-differentiable because there's a kink in that graph at that point. And we can see that this is a cusp because the concavity is concave down and stays concave down. Okay, because we can't actually evaluate the concavity at 0, so it's a non-differentiable point. However, we can see the concavity on both sides of that.